Colloquium. Today is our pleasure to have Edgar Shaghoulian. He obtained his PhD at Stanford, and later on he did postdocs at Santa Barbara, Cornell, and the University of Pennsylvania. And he's now a professor at UC Santa Cruz. And his research interests are quantum information and formal aspects of quantum field theory. And today he's going to talk about the central dogma horizon in quantum cosmology.
Thanks, Fabio. Thanks for having me. I'm going to talk about quantum cosmology, but since it's a broad audience, it's going to take me a while to build up. So 75 to 80% of this talk is not about cosmology, depending on how many questions, potentially 100% of the talk. But let's dive right in. So this is maybe something near and dear to the hearts of people here. We have lots of spectacular data on black holes nowadays. These are the Event Horizon Telescope images. And here's the first gravitational wave signatures from LIGO. And we also have great data on cosmology here, 3 generations of the CMB anisotropy maps on the left. And here's the Wikipedia image of our best understanding of the evolution of our universe. And the 2 things I'm going to be motivated by here are the current phase, the late time phase where we seem to be beginning to accelerate, sometimes called the dark energy dominated phase. We also believe we had an accelerated phase early in our universe, known as the inflationary phase. Okay, these situations are fascinating partly because the laws of physics, as we understand them, break down in both these cases. They break down in black holes and they break down in cosmology. So that motivates the problem of trying to understand quantum effects in gravity to avert this kind of breakdown. Okay, and I'll start off with the case of black holes because they're particularly interesting. It's a situation where we expect gravity and quantum mechanics to be reliable, yet they give sort of inconsistent or nonsensical answers. This is known as the black hole information paradox. And I'm going to be talking about one aspect of it, which I'll develop, and then talk about how we want to use what we've learned in this context in the case of cosmology. So let's jump right in. Start off by saying something which is maybe offensive to this audience. A classical black hole is a pretty boring object. Okay, it's most of what's interesting and beautiful about it is its interactions with its environment. Okay, that's a lot of the data and stuff that we look at has to do with that. But if you tried to isolate a classical black hole, it wouldn't really do anything. Just sit there, and nothing interesting would happen. This is part of a letter Schwarzschild wrote to Einstein. He was a little too optimistic. The war did not treat him kindly. He was dead within a year. But for a while, he enjoyed, playing with the equations. And he discovered the first black hole solution in general relativity. A quantum black hole, as first described by Hawking, is a much more interesting object in this sense. You can't, you sort of can't isolate it from its environment. It's not just going to sit there. It's actually going to evolve. It's going to evolve by emitting Hawking radiation. You think of just as a particle that's entangled with some buddy partner on the inside. And as it does that, it shrinks down. It loses mass, it shrinks, it continues this process until we believe eventually fully evaporates away, leaving just the Hawking radiation. Okay, that's fascinating. Another fascinating thing about this picture is that these black holes, these quantum black holes, seem to have a temperature and an entropy. Okay, like a gas in a box. The entropy formula is quite bizarre. It scales with the area of the black hole, so it's not extensive as you may be used to from statistical physics. And another reason we're fascinated by this formula is that it combines all these fundamental constants. I'll be setting these to 1 for the rest of the talk, but it seems to combine these various branches of physics. Okay, that motivates asking the following question. If it has a temperature and an entropy, like a gas in a box, does it have an atomic description, like a gas in a box? Okay, Boltzmann provided this atomic description for gases and more general systems back in the day. And in this talk, I'm going to be assuming something that it's an old idea. I'll call it the black hole central dogma in this talk. And it's the idea that from the outside, you can think of a black hole just like an ordinary quantum system, like a gas in a box or something like that. The only slightly weird thing about it is that its Hilbert space dimensionality is given by this formula that you saw earlier. But otherwise, it just kind of evolves unitarily. It's an open system, it interacts with this environment, but it's just an ordinary quantum system interacting with this environment and evolving. Okay. I call it a central dogma because it's an assumption. We don't know that this is true, for example, for black holes in our universe or general cases of black holes. But there's a fair amount of theoretical evidence for it. I think the strongest starts with some calculations that were done here, where certain special black holes, you could count microstates in a Hilbert space and reproduce this formula. Okay. And since those original calculations by Strom and Jorvapa, there have been lots and lots of generalizations. And actually in the past several years, it's actually resurged as people were able to tackle even more general black holes. Still not the ones in our universe, still very special, but there's some evidence for this part of the central dogma. Okay, so that's great. Quantum black holes seem to have lots of cool, interesting physics, but they also famously cause us a problem. So the Hawking process, which I described, it creates entanglement between the Hawking radiation outside the black hole and the partner buddies, inside the black hole. But then the black hole evaporates and it's gone, seemingly taking with it the little entangled partners. So here's just two representations. On the left side is just the Penrose diagram for an evaporating black hole. You could imagine this as the exterior Hawking quanta, the green guy who's entangled with its green buddy on the inside, blue's entangled with blue. And if you go to a sort of late time Cauchy slice, which you end here, then you only have access to the green and blue guys on the outside. So you could have, for example, started with a pure quantum state, let's say a star that's collapsing, that's what this orange blob represents. And it would evolve in this way to a mixed quantum state because you don't have access to the partners of these entangled particles or qubits or however you want to think about them. This is just a more schematic representation of the same thing. Time's going up here. Here's the blob that collapses to form a black hole. So black hole appears at some time, and at late time it's gone. And if you're some exterior observer with only access to the outside, you only have access to part of the entangled pairs. So something like this is going on. And that is a violation of quantum mechanics in the exterior of the black hole. Okay? Pure states are not supposed to evolve into mixed states. If you evolve them with an ordinary Hamiltonian, e to the IHD, they'll just evolve to another pure state. This is not supposed to happen.
Why do you qualify this violation of quantum mechanics in the exterior of the black hole? I just say the violation of quantum mechanics full stop.
Well, I say that because if you wanted to add, part of a Cauchy slice that's somehow in the interior of this black hole, and you're some sort of meta observer that has access to all of it, and you want to think about the Hamiltonian that evolves that, then pure states will evolve to pure states.
Well, but I would say if you want to think of it like this, then you're always seeing a mixed state in the exterior where the black hole evaporates or not. So the point is, the reason that it's important that the black hole evaporates is that we don't get a unitary S matrix.
Yeah, from the perspective of S metrics, I agree. That's like restricting to an exterior observer, but that's why I say the exterior of the black hole, the S matrix is an exterior object.
I guess I would contest this statement that you're restricting anything to an exterior observer simply because of late times there's no other kind of observer. The entire universe is literally the black hole exterior because the black hole is disappearing.
I morally agree with you, but I just want to leave open the physical point that if you wanted to supplement some Cauchy slice out here with one in here, then the state on that slice, and maybe that's what you want to do to write down your fundamental description. I don't think that's how the fundamental description should be written. Well, we don't, I don't know that we know. I don't know that we know. In the general case, I don't know that we know how it works. I'm sympathetic. I think it should be defined by data very far away, but if you're in a closed universe or something, who knows?
Yeah, I guess I would say that if you need to use the black hole exterior to purify the late time radiation, that this is tantamount to information loss. But maybe we're just talking semantics.
Yeah, I'll leave it this way. I don't want to add this exterior thing. I mean, all I think you're saying is that this is just necessary for a fundamental description.
This weaker statement doesn't rule out the stronger statement.
I agree. I wanted to make my opinion known that little bit there is not needed.
Yeah. But
Very
you don't
good.
think it's wrong.
I don't think it's wrong. It's just I think it's being too cautious.
Okay. Been blamed for a lot of things, not often that one. Okay. So we can make this a little bit more precise. The way I phrased it here, we compared very early times to very late times, before and after the black hole's life. We could make this a little bit sharper. To make it sharper, we think about it the following way. Take the Hilbert space of your entire system and break it up into two pieces. One that corresponds to the black hole degrees of freedom, and one that corresponds to the radiation degrees of freedom, R for radiation. Okay, in certain toy models of black hole evaporation, you can actually do this precisely. And again, we're going to assume the central dogma. We're going to assume the dimension of the black hole Hilbert space is given by this formula. And now we want to compute the entanglement entropy. Okay, what's the entanglement entropy? Basically, you trace out the part of the quantum state in the black hole Hilbert space to produce the density matrix for the radiation part. Form this combination. You take the trace, you stick a minus sign on it. That's the entanglement entropy. All right. Generally pretty hard to compute. There's a simple bound that comes from quantum mechanics, which looks like this. Okay, how do we understand this bound? Well, all the bound is saying is that you can only be as entangled as there is stuff to be entangled with. Okay, the part of the state here is entangled with stuff here because that's the full state, and the stuff here is limited. It has a finite number of degrees of freedom, so you can only be so entangled. That's where this bound comes from. And one aspect of the information paradox is that Hawking calculated this quantity and found a violation of this bound. Okay. And remember, let me point out that this assumption here is fundamental to saying that there's a problem with this bound is violated.
But let's see, so in addition to the central dogma, you're also assuming now that the microstates is exactly the area equation, right? They're not exactly the same assumption.
That I included that in the central dogma.
Oh, you
The Hilbert
included
space is given by this formula.
Oh, I thought you were just assuming it was unitary.
No, this was the biggest part of the assumption.
I see.
That's why your calculation was evidence for the central dogma.
So is the tensor product factorization part of the assumption?
That's not in the central. I mean, to make sense of this, you need to do this. And in certain toy models, you can do this precisely. For again, a black hole evaporating in our universe, people will argue about whether this is a reasonable thing to do. But in certain toy models of black hole evaporation, you can do that in a rigorous way.
Okay.
Yeah.
So I thought that you were stating the central dogma is something that everybody would agree with,
Oh.
or almost everybody. Say,
Okay.
I
thought almost everybody would agree.
Well, but I mean, aren't there some people who, I don't know what I think, but aren't there some people who think that, maybe the information is in the ergosphere outside the black hole, or, it's a much more precise statement, isn't it?
Well, I guess
this is a stronger statement than what Page would say, that the black hole evaporation is unitary and so on.
I mean, I guess I didn't specify that like the black hole degrees of freedom, that this Hilbert space like lives right on the horizon or anything like that. I kind of vaguely said the black hole Hilbert space, whatever that may be.
Okay,
Of course.
so this could go out to the photon ring, for example.
Yeah, in these examples, for example, if you have a black hole in ADS, it goes all the way to the ADS boundary.
Right.
So I didn't specify where that lives exactly.
I see.
I was ready with an objection as well, but then I noticed at no point did Edgar say this area of the event horizon or this of the event horizon.
We don't. Oh,
No, this is the area. This is their area of the event.
Sorry,
Yeah.
I mean, okay, that I
Yeah.
object to, but I think I know. what
Not
you
the
mean.
apparent horizon.
But,
Okay. Got the audience. Yeah. Okay. Any other? All right. So, okay, Hawking calculated S of R. What did his calculation look like? It looked like this. Let's say you plot the entropy as a function of time. As the black hole is evaporating, it's emitting Hawking quanta. So its entropy, Hawking found, just kind of increases monotonically until the black hole is done. And then it, sits there because it doesn't produce any more Hawking quanta. On the other hand, the area of the black hole is shrinking during the Hawking process. And eventually, again, we believe goes down to zero. And there's a problem right when these two curves cross. Okay, you don't need to wait till the very end. There's a problem already at that point. All right. Some of us don't like this. Some of us don't like this. We think quantum mechanics should behave this way. Don Page in particular didn't like it and argued in the early 90s that a quantum theory of black holes should instead follow a curve that looks like this. It very closely follows Hawking's curve in the early parts and has a pretty sharp turnaround and follows the area of the black hole all the way down to zero. So it kind of almost saturates this bound set by quantum mechanics but otherwise is safe. So he argued just by thinking about pure quantum mechanical systems, he wasn't really playing with any gravitational models or modeling them by pure quantum mechanical systems. He argued that it should look like this. Okay, this is just a signpost in a sort of decades-long debate that's still going on about whether black holes respect quantum mechanics and the information paradox. I'm going to focus on this aspect of the information paradox for the next several minutes. Okay, we're going to try to compute it. I'm going to take a sort of a chronologically backwards way of computing this entry, but then I'll come back to the original calculations. We're going to use the gravitational path integral to try and compute this page curve, okay, which is what we call the curve we think is correct for the quantum mechanical entropy of the Hawking radiation. Okay, what's the gravitational path integral? Honest answer is we don't know, but it's written down a lot like the ordinary quantum mechanical path integral. So what do you do there? Well, the path integral lets you compute all sorts of things, for example, correlation functions. And the way you do them is you integrate over all paths. So you want to ask about a particle going from the initial position to the final position. You put those boundary conditions on your path integral. You integrate over all paths consistent with those boundary conditions. You weight them with the action in this way. And you do this integral if you're powerful enough. Usually, you're not powerful enough, or I'm not powerful enough. So we evaluate it by saddle point. And the classical limit as h bar goes to 0. You evaluate by saddle point, which means you look for extrema of this exponential. The extrema are the points of minimal action. So you're really looking for the classical solutions to the equations of motion. Okay. Field theory is written in a similar way. Instead of paths of particles, you have quantum fields. You set some, let's say, initial and final conditions for the quantum field and integrate over all field configurations in between. But otherwise, it's the same sort of object. And you can write down quantum gravity in a similar way. You add the metric as an additional field. Now things are getting a little bit crazy because you're integrating over all sort of space-times in between some fixed initial and final boundary conditions. But schematically, you could think about it in a similar way. Now, these objects, as you may know, are pretty gnarly. Even this object, to make mathematically rigorous, is very hard, except in the simplest of field theories. This object, forget about making it mathematically rigorous. We don't even know how to make it physically rigorous. Okay? We don't know the rules of this object. There are some rules that we like and we use, but it's still an outstanding issue to understand this guy, and it has various problems, actually. I'm going to avoid most of that in this talk because I'm just going to evaluate this by saddle point. I'm going to look for solutions to the equations of motion. Even there, you can quibble because before you can figure out which saddle points are allowed in an integral, you need to know what your contour is, etc. And that's part of the problem in defining this object. But I'm going to assume any saddle we find is allowable. That's an assumption.
But even though we don't know the description, it's assumed that because we have say like a string theory that there exists some description that is appropriate for energy description.
I think we assume there exists some prescription, yes, but it's hard to, even in the low energy theory, to make such a prescription reasonable. Because it's a conformal mode problem in general, to figure out whether you sum over all topologies, which I didn't include such a sum. There are questions like that we don't really know the full answer to.
So we don't even really know what this thing is computing.
It's computing. Well, yeah, given that we don't know what it is, I guess that implies that we don't know what it's computing.
We don't really know what we'd like it to be, in certain cases.
Well, but in ADS-CFT, there's a boundary definition, and don't you assume that both have some definition like this? Or?
Yeah, in ADS-CFT, there's a boundary definition. We can make this precise by just saying that, well, you do the boundary path integral, and then you're in this situation, which we understand better. At least at the physics level, we understand precisely. Mathematically, again, it's tricky. But we don't have a natural bulk way of writing this. In ADS-CFT and holography, that's one of the reasons we believe we should, for example, sum over topologies, because if we didn't, we would get answers inconsistent with the boundary field theory picture. So there are various pieces of evidence of how to do this coming from ADS-CFT, but we don't really know the final story about it.
Right,
But also, I mean, even self-consistency is a pretty powerful constraint.
Yeah, in what, guys?
Well, I'm, you know, if you start doing settle point approximations to this. If you get it wrong, you could easily run into self-consistency is already very strong.
Right. Yeah.
Yeah.
Yeah. I agree with that. Okay. So let's go ahead. So you can use the path integral to evaluate all sorts of things. And I'll give a schematic version of what the calculation looks like for computing something like the entropy of the radiation. So you're gonna have another representation of a black hole. It's a time slice. Here is again the star, whatever collapsed to form the black hole. Here are the interior Hawking modes. Here are the exterior Hawking modes. And first, let's do the computation in classical gravity, okay, with quantum fields. This is like a quantum field theory in the curved spacetime sort of problem. And so your geometry is fixed. Okay? You only integrate over the quantum fields. And you integrate them over this sort of spacetime to compute something like the trace of the density matrix of the radiation. Okay, so you do this path integral, and that's supposed to spit out for you some answer. The geometry is fixed. If you want to do the quantum gravitational problem, like I said, you need to fix some boundary conditions. So what that looks like, roughly, is you fix your geometry very far away, or some region, and then you're supposed to integrate overall geometries consistent with that boundary condition. Okay, so that's why I wrote geometry is fluctuating here. That's hard. It's just that these integrals are hard to do. So we're going to evaluate it by saddle point. We're going to look for a solution to the equations of motion consistent with these boundary conditions. Well, there's a solution. Okay.
These are
And-
Euclidean pictures.
Sorry.
Are they Euclidean pictures?
I mean, when we do the, what do you mean by Euclidean pictures? It's always a little subtle. What do you mean by
What the pattern, the bulk pattern that you wrote down earlier is a Euclidean. You're writing a Euclidean. thing.
You're making, yeah, you can think about
minus
doing
s until I.
in that sense, yes, it's a Euclidean integral. I mean, you're going to be able to access things in Lorentzian time by appropriate analytic continuation. But yes, you're doing the e to the minus s sort of Euclidean integral. That's what we do. Okay, so we want to look for a solution. I said the solution is one here, so there it is. That's the one solution with the fixed boundary condition. So quantum gravity doesn't do anything interesting here. All right, to leading order, it gives basically the same answer. Okay, boring calculation. Things will get more interesting if you compute, instead of the trace of the density matrix, the trace of the square of the density matrix. Why would you want to compute this? Well, this is something in quantum information theory called the purity. Why is it called the purity? Well, simple reason. If you have a pure state matrix, it looks like this. If you square it, it doesn't change. The trace is 1. If you have a mixed state, let's say what you get by tracing out one qubit in a Bell pair, the eigenvalues are going to be less than 1. So you square it, they're going to get smaller. The trace is going to be less than 1. So the purity is measuring how pure your state is. If the trace of rho squared is 1, then it's pure. Less than 1, it's impure. And in these gravity path integral sorts of calculations, because you're doing trace of rho squared, in a sense, you have 2 copies of rho. So you need 2 copies of your state. The way this translates into the path integral calculation, here I'll just jump to the quantum gravity version, is you need 2 copies of your boundary conditions where you fix the geometry, and then you integrate over all geometries that are consistent with those boundary conditions. All right, now things get interesting. Again, we're going to evaluate it by saddle point. One answer is 2 copies of what we had before.
Is that the same as you want to do the experiment twice? What you mean like
Sort
you
of,
put,
yeah.
you put boundary conditions on square minus or something, and it would be the same state.
Yeah, you need to like form the black hole twice or something if you wanted to trace rho squared.
Right.
Like, yeah.
But this is all a fixed moment of time.
These pictures aren't great because this is a time slice picture of a Lorentzian evolution. But yeah, you can develop the thing I'm computing is a function of time. So this is what the computation would look like at a particular instant in time.
Okay.
Yeah. Yes.
Sorry, so the idea that in full gravity theory, there might be other geometries that are consistent with those boundary conditions, but just in the semi-classical approximation, we just have one solution for DR. Is that what the idea is?
Yeah, I mean, I'm going to have another solution right now, but yeah, you just look for the solutions, and that in this leading order and H4 goes to 0, those are the solutions you should worry about. So here's one solution. Shouldn't surprise you from our discussion before, but in this case, we actually believe there's another solution. Okay, and it looks like this. It's a wormhole that connects these two geometries. And when you do integrals by saddle point, if you find more than one saddle point, you add them. Again, unless there's some subtle reason why you shouldn't include a saddle point depending on the contour. In general, in physics, we just always consider all saddle points, and unless it runs into a problem, then we rethink. But here we'll include these two saddle points. In toy models where this is calculated, there are additional ones you could worry about, but these are the leading ones that we need to worry about. This one I'll call the wormhole saddle for obvious reasons. Wormhole. This one I'll call the Hawking saddle, basically because if you ignore this one and only consider this one, then properties of the density matrix of the radiation that you would compute would be consistent with how Hawking would compute them. Yeah.
So is that one like, if this is GR, right? So in the Hawking calculus, is that like a double eternal force shield where you have both sides?
Yeah, it's like
The
that.
one on the right is not that.
That's right.
Okay.
Yeah.
Is it? I'm actually somebody to do our elementary point here. So is it a, I mean, I think it's a reasonable hypothesis, but is it a hypothesis that having these two disconnected boundaries computes trace rho squared, or can you derive that from something like doing an experiment twice?
I think it derived from doing experiment twice. So the rule here is the rule for just computing like entropies in quantum field theory. So I've left out some details. For example, I haven't written down the cut and the gluing of the two things that compute for you entanglement entropy in
Right.
quantum field theory. But
Right.
that's kind of going on here. There's some cuts that are actually glued together via those cuts,
Right, but
and that's supposed to.
but as you know, that involves kind of an analytic continuation from the integers, right?
I'm not there yet. So right now I'm just computing trace rho squared. And for that, you make I'm not at the level of doing entanglement entropy. I'm doing this quantity. For that, you just make two copies, you glue them along some cut, and then you do the path integral.
Okay,
But you'll be able to complain in a few minutes when we get to entanglement entropy.
I'm not complaining, okay.
I'll complain. So this is, you said, if you could say this is a moment of time, but that's the thing that goes into wormhole, that's a space-time wormhole, not a space-time wormhole.
Yeah. Yes.
So that's not a moment of time, what you're drawing on the right.
Well, in the space-time wormhole, you could cut. Well, if you do a way, you can cut a space-time wormhole into a spatial wormhole. So in this case, you can draw something that roughly looks like this.
I think that you can only do that in 2 dimensions. If you're in any.
Yeah, these are
more
two.
dimensions, it's not gonna look like that.
Um,
So, okay, I don't know what's gonna look like
Well,
because they're high dimensions, but.
Yeah.
I mean, it's kind of critical for this thing to be connected in time, I would think, for the space-time wormhole. I mean, it's a critical part of the story.
I agree, but these pictures are a lot prettier than the ones I would have drawn for that. I think you would agree with that. Because see, I have the black hole here and there's a wormhole inside. Yeah, I should say these computations that I'm kind of alluding to are done in simplified 2D models, which is the case where we can actually do any of these computations.
2D, 1 plus 1 or 2 plus
1 plus 1.
Well, that's not entirely fair, right? Jeff did a calculation that showed the same thing in higher dimensions.
I'm not, yeah, well, that calculation's a little weird.
I think it's pretty good.
We make some, okay, well.
Sorry,
we
how
could
is this 1
scribble
plus
about
1? What, the cross section of this is a circle, right? I realize it's not a circle.
No,
1 plus 1 is a point.
that. The picture is not a 1 plus 1 picture. I'm saying when we've actually done the computations
Oh,
are in 1 plus 1 models. The picture is a higher dimensional picture just because it's.
the picture is 2 plus 1,
Yeah,
right?
yes.
It's a moment of time, yes.
Yeah.
What is it? Wait,
Well, it's not, that's what I was saying. This is
The one on the
space-time
right.
wormhole.
yeah,
Yeah, so this is the event horizon. It's like a circle. The red
Yeah.
thing.
okay.
So it's a 2 plus 1.
It's a cross section of a 2 plus 1. Oh, it's a cross section of something that computes trace rho squared and 2 plus 1.
Yeah.
That's what you're doing.
Yes.
Yeah.
Yes. Okay. So these are the two saddles, and you're supposed to sum them. And the point is that at late times, the contribution of these two saddles is a function of time, and at late times, this one dominates, and the trace of rho squared goes to 1. I haven't normalized these carefully. If you normalize them, you get that this goes to 1, up to a small correction. And so you see that the state becomes pure at late times.
Whoa. Wait, I thought this was at a moment of time.
Yeah. So these are pictures at a moment in time, but you can draw similar pictures at any moment in time as you evolve. The way the time dependence of that picture is that the cut that you do and glue these two copies through the cut is going to include different things. It's going to include more and more Hawking radiation. So the contributions are a function of time, such that this one becomes the dominant one at late times. Okay. So I did a bit of a bait and switch. I talked about the page curve and entanglement entropy, and then I went and computed this funny quantity. So let's go back to talking about the entanglement entropy. And there's a remarkable formula that was written down for the entanglement entropy by these authors.
Edgar, Are
Yeah, yeah.
are you really saying that's been shown, or what, are you asserting that, or?
Which
Something-
thing? This,
Yeah, that the wormholes dominate at like time.
yeah,
And
so,
certainly we didn't show that in our paper.
right, yeah, so the, yet another subtlety which I'm glossing over is that what I'm drawing here is some solution that exists for having two copies of the space-time and gluing it this way. And I think except in like one special case, which I haven't even checked the details of, it's difficult to find solutions that look like this. Really what we do is we work at an integer number of copies, n equals 2, 3, 4, however many, and then we do an analytic continuation to work for n near 1, and for n near 1 you can find a solution. So-
Nowadays, I think that people have constructed solutions of the two boundary.
Yeah, who's done that besides your
so my
Bob?
guy,
Yeah,
an
that's the
example.
one that I haven't looked at the details
Yeah.
of, so I can't surely
I
say
think
that.
it's pretty robust.
Okay.
Yeah.
Okay, I believe you. Yeah, but even that is just, yeah, it's just like literally this two boundaries, not like 3 or
So
4.
it's just choose.
Yeah.
He has a nice analytics solution to two boundaries.
Actually, are they real, the solution? Yes.
At late times, they should be generally complex.
Do they satisfy, there was this rule that Whitman was talking about, that to rule out the bad metrics and the good metrics,
Yeah,
there was a rule about if you have a complex metric.
yeah.
the-
I suspect it's that, yeah, I suspect it satisfies that.
Okay,
Sorry, I don't think the metric is real. The sources are not, the sources for the metal are not real, but I think the metric is. I think everyone's paper was all about complex metrics.
Right.
This is a real metric
Yeah.
with complex sources.
okay.
At late times when the black hole is very small, why can they use the subtle from the parts machine?
Very small, you mean like Planckian?
Mass support the calculable, the black is done with simple subtle point.
So you mean when the black hole is Planckian? What?
Yeah.
They're okay. We don't, I mean, we really can only track the curve until it becomes Planckian, but like I was saying, this problem appears in the page group, is right around the turnaround point. And you can take a very, very massive black hole if you want and track this curve till very, very, very late times. At the very end, okay, you can't really reliably say something. You just kind of assume that it smoothly goes down to 0. But you can still track like as much of the page curve as you want by making as big a black hole as you want.
Of course, this black hole is not actually dynamically evaporating because you're assuming there's a work rotation to go at the same time. I mean, you're not actually taking a black hole from collapse,
That's right.
then evaporate it. And you're not looking at this page curve. You're looking at
Yeah, that's
the
right.
unitary behavior of the entropy.
Yeah.
You're never going to end up in a situation where this thing is plankton.
Yeah, I mean, I was answering the question for like, if you did this computation in an actual evaporating black hole and the page curve looked like that, then we wouldn't be able to say anything about the very, very end.
Right, I mean, like if you did a starvation with your Felders type calculation.
Yeah. Okay. So let's return to, let's I'm forward this formula for entanglement entropy that was first written down by these authors and was the first way that entanglement entropy for the radiation was computed. And the formula looks something like this. I've simplified it a little bit, but basically you take two options and you minimize between them. Okay, one option is that to compute the entanglement entropy of the radiation or just some region R, you do the ordinary quantum fields and curved space-time sort of problem. You compute it the way Hawking would have computed it, and that's one option. Another option is this kind of crazy looking thing where you allow yourself to include what are called island regions denoted by I. These are codimension 1 regions in the space-time. You form this combination, and I've left out a crucial thing, which is that this combination should be an extremum with respect to variations of the boundary of I. Okay, that's technically the hardest thing to show and deal with, but I'm going to ignore that for the purpose of simplicity. And if you have such extremum, you include that as one of the options in this list of options. You can have many possible island configurations. Okay, And if you have them, then you minimize between these two options. Right, that's the formula. That's how the page curve was initially computed by these authors. And one way to think about what I was just talking about with the gravity path integral is if you assume the gravity path integral, then you could think of deriving this formula from that perspective. And this type of saddle is giving you this kind of option, and this type of saddle is giving you this kind of option. Okay, that's where you could think of these two terms as coming from.
Is there an argument that the second option is one that a detector would measure? There's two different things you could compute.
Yeah, it'd be the one that the detector would measure. I guess if you did these multiple kind of experiments, if you formed many from black holes and computed what's it called, the swap entropy. If you computed that, then this is something that would contribute to that. It's similar to, I guess, what you would say just about entanglement entropy in the lab if you wanted to compute that. It's
That's not true in 1+1.
What's not true in 1+1?
The second thing is what a detector would measure.
Why?
We wrote a paper on that.
Oh, you mean if you don't use the gravity path?
We use the gravity path.
Not in this way.
We followed the usual rules of quantum mechanics. And
Yeah,
and
but you're not the
we
rules of
did-
the gravity path integral.
No, the gravitational path.
Sorry, is that different from the gravity?
This is the paper you and I were on.
I know, I understand. But
And
there,
we say in the introduction that if you follow the usual rules of quantizing gravity and quantum mechanics,
yes,
doing systematic 1/n expansion, you get the left-hand side, not the right-hand side.
I agree. Yeah, that's following the rules of canonical quantization. That's the thing.
The standard rules that anybody would.
Yeah, but the rules of the gravity path integral are inconsistent with those rules. I think that's one of the interesting things about the gravity path integral. That if you quantize things that way, you don't allow non-trivial space-time topologies.
So should you be concerned that you're proposing rules for the gravity path integral that do not agree with the soluble in a soluble system, do not agree with what you get in the soluble system?
I think you should be concerned, but I have more faith in the rules of this kind because they are consistent, for example, with the rules in holography and ADS-CFT.
So,
Whereas
so if you have a system where you can solve it exactly in a systematic small parameter.
Yeah.
And then you have some approximation involving saddle points in a complex plane. You would take the latter one over the former?
Yeah, absolutely. It's a question of which.
Okay.
It's a question of which thing you think, which model you think is relevant for describing higher dimensional black holes. So, for example, if you believe in the
Well, now you're saying something different. Now you're saying that that you agree that it's not true in 1+1.
well, 1+1, I completely agree that there's a way
A
to
moment ago, you said that in 1+1, the gravity path integral also gives
you this. Yes,
the right-hand side.
yes.
Okay, but that's a
Quantization
system you
does-
can solve and you can show, as we did, that it doesn't give you that.
Well, you solve it via some rules, right? We don't know what the rules are. for-
These are the same rules that everybody's been using for the last 4 years to solve systems in 2 dimensions. It's not that hard.
Yeah, you canonically quantize, but we don't think that that is describing.
No, you can use Feynman diagrams, you can use any method. It's a CFT. You can
Yeah, but you
use it
can't
with
use this
CFT.
gravity path integral in the way that I'm talking about here, where you sum over space-time topologies. That doesn't work. I agree it's under less control, because when you do it the other way, you can solve it exactly. But when you do it that way, you get
So
results.
if you have 2 ways of doing a calculation and they don't give the same answer, shouldn't you find the flaw in one of them? A
I don't think-
proposed flaw?
I don't think there's a flaw in the way you do the computation where you end up with this. It's a consistent system where you just have this saddle and you do it by the usual, let's call them the usual rules of quantum mechanics. But you get results that I think many people don't like and seems inconsistent with ADS-CFT. In particular, for the black hole entropy, you wouldn't get A/4G. So
Well, that's the puzzle. You, that of course is exactly the information puzzle. But
I
yeah.
have-
yes, yes. But okay, so one other perspective is when you get answers that disagree with the Bekenstein-Hawking entropy or things that we believe are true from ADS-CFT, like summing over space-time topologies, then that's a reason to question that procedure, which works for quantizing all
Okay,
non-gravitational.
so,
circumstances we like.
so we have no reason to think that the sum of the wormholes is guaranteed to give you unitary, crossing symmetric, answers, right?
No, no.
It could do anything.
It, well, could do any, yeah, we haven't understood the rules of it. So because we haven't totally understood the rules of it, we don't know what it's going to spit out. Tomorrow, someone could do a computation, include wormholes, and get a crazy ass matrix or something. We don't know yet.
I mean, maybe you say something, I'm not, actually not disagreeing with you, Andy, but, if you just take the gravitational path integral out of this story for a second, and you just say you have two ways of computing the moment entropy in ADS-CFT. One is the moment entropy of the Boole quantum mechanics, and one is the moment entropy of the boundary, which is quantum mechanics without gravity. Since we are more ignorant of the rules of gravity, quantum mechanics and gravitational theory, we would prefer that the answer that we get.
I
be
think
consistent
people
with the
are
boundary
pretty
quantum
confident going back to the 80s that we understand gravity in 1 + 1 dimension.
mechanics.
The causal structure doesn't fluctuate.
Right.
And, there are thousands of papers on that, which,
So I think
which,
you're
which
getting at-
all tell a self-consistent and very detailed with lots of precise formula, story. And what Edgar is saying here is we should throw all that out.
Well, I think
And
I think, I'm
Based
not
on-
saying, well, I think ADS-CFT threw all that out. Those theories are inconsistent.
ADS-CFT is a very different problem. That's in, I think the black hole information problem is parametrically and qualitatively different in ADS-CFT than in flat space. Because in flat space, which you started out with, right? In flat space, the information problem is a problem of order 1. You start with a pure no entropy, and you end up with the maximum entropy. In ADS, black holes don't evaporate; they're like the remnants, and so the real information problem is exponentially small corrections to correlators. So it's quite plausible that an ADS non-perturbative exponentially suppressed effects could wormholes could, and indeed I think that's true. I think it's true in ADS that this whole story is correct. But I think that it's qualitatively different. And of course, it's completely clear that holography is qualitatively different in flat space than in ADS. So I think there's a huge jump here where you say you're doing this, you're redoing the flat space calculation to make it look more like the ADS one. I mean, I think ADS is fantastic, but I think we need to think about some, that there are other.
Yeah. I mean, this calculation, for example, hasn't been done in the most general way, but let's say you wanted to create a small black hole in ADS and then watch it evaporate. So unless you think that a small black hole in ADS, meaning much smaller than ADS curvature scale, the physics of that is very different than a black hole in flat space, then
I think there's a phase transition between large black holes in ADS and small black holes in ADS.
Okay.
And we don't even know what a small black hole in ADS corresponds to in the boundary theory. And we've been struggling with that for 25 years. And the very fact that we haven't been able to solve that problem, I'm sure you've tried, I've tried, but the very fact that we haven't been able to solve that problem is more reason. We can't claim to understand how information comes in and out of a small black hole if we don't even know when we have one. So basically ADS is giving us no information about small black holes. And the very fact that we've tried to solve that problem for 25 years and failed, I think is more evidence that the information problem is qualitatively different in flat space than in ADS.
well, I was going to make a minor technical point about small black holes in ADS, is that if you think that they exist and are described by the field theory, we don't know how, but if you believe that they are, then along for the ride comes the following statements, for example, that there are not supposed to be any global symmetries in the bulk. And these 1 + 1 models, where you can quantize them exactly, are inconsistent with that. They have global symmetries, at least all the ones that people have studied. And so they have features that you might also question, even though the rules are very clear and it's a self-consistent system you can solve and study. There's some weird things about it, but
Well, I agree with that. I'm much more sympathetic to the statement that the 1 + 1 models of black holes don't exist than that they do exist and are described by the Island Bill. They might just not exist all. And also there's evidence that the 2 + 1 theories also don't exist. Well,
Yeah.
not the ones that aren't embedded in higher dimensions.
I mean, my perspective on this, which I'm going to come back to in the, well, okay, I'm gonna
I should
pause.
probably shut
And just proceed, because, well, because I'm not gonna make cosmology, but that's totally fine. I wanted to talk about how you apply this formula to set us up to talk a little bit about cosmology. The way we believe it's supposed to work in an evaporating black hole is that you start off, the black hole's formed, okay, hasn't emitted any Hawking quanta yet. And when you do this minimization between these two options, you pick up this option at the beginning of the black hole's life. The entropy of the radiation is 0 because there is no radiation. The black hole area is as big as it's going to be. And then the black hole evolves and spits out Hawking quanta. Its area goes down, the entropy of the radiation goes up. The formula is still given by this choice. It stays there. And then you're about to run into the problem we're talking about, where these curves want to cross. And right when that's going to happen, the formula switches from this option to that option. And the curve actually follows instead the area of the black hole. Okay. Now, I'm not going to argue about how you see that this is an extremum with respect to variations of the boundary of I, but we can see easily why it's less than this option. To see that, let's look at the formula. I corresponds to the region inside this red circle. So R union I is these Hawking modes combined with the interior Hawking modes. So that has 0 entropy to leading order. But there's also this piece, the area of the boundary of I. That basically sits at the horizon at leading order. And so that's why it follows the area of the horizon divided by 4g Newton. Okay. And then once you pick up that piece of the formula, it just stays there. The entropy decreases until, again, we believe totally evaporates away and hits 0. Okay, so that's how this, sometimes called the island formula, was shown to give an entropy curve that looks like this. Yeah, let's go through that one more time in a slightly different way. The formula switches from one option to the other. From the gravity path integral perspective, you could think of it as an exchange of dominance of saddles. And in a Penrose diagram picture, you can think of time as being like some null time here, and you measure the entropy of modes coming out. And at first, you just have the QFT entropy of R, and then at some time, the page time, something weird happens, which says you include some island region in here and compute instead this quantity. Okay, this was believed to happen. So that's very weird. Why, when you compute the entropy of this, do you include some space-like separated region inside the black hole? I'm not going to say too much about this, but it is kind of pointing to a sort of non-locality, and the best way we have to explain this is that it's a bit like holography, or how information is encoded in holography. In particular, the interior of the black hole is believed to be encoded in the Hawking radiation far away from the black hole. And when we say it's encoded, what we mean is if you have some operator that you want to act inside the black hole and flip some qubits or do some funny thing, you can instead act with some very complicated operator on the Hawking radiation far away and achieve the same effect. Okay, there are lots of subtleties in this statement, but that's the rough idea. And it's how information we understand is encoded in holography. It's going to be important for when I get to cosmology. Yeah.
It was like similar to the space like separating Hawking radiation, that's like in the black hole complementarity, where you have the effect, like I forgot the membrane outside of the black hole, and then Hawking radiation the black hole is off before the black hole starts to evaporate. Is that what?
I never really knew what complementarity meant, so it's a little difficult for me to answer that question. But I think people think that this is some realization of complementarity. I don't know. It's hard to say anything about it because the statement was never made precise. Okay, I think this is a source of non-locality in quantum gravity, which is interesting to understand. Engelhardt and collaborators have studied this recently. Lots of other people are thinking about how to think precisely about this non-locality. But what I want to say, which may draw some objections, is that this Hawking style formula has been applied in all sorts of cases, but from the perspective, I probably should have put this on slide, from the perspective of the gravity path integral, it's wrong. Okay, it gives you answers that are inconsistent with ones you'd get from applying the rules of the gravity path interval. So you can ask, where else can you look to see, what kinds of new answers can we get applying the rules of the gravity path interval? And that is what's going to bring us to cosmology in the last 8 minutes. Okay, I think it's an exciting subject. I think that I just picked the sort of selection of papers mostly focused on things people have done recently, somewhat inspired by what's been going on with black holes. Okay, there's a lot more papers, but people are trying to apply some of the things that we've been applying to black holes in the case of cosmology. So let's review the structural similarity of black holes and in particular accelerating cosmologies. Here's a black hole, space is collapsing inside, so there's an event horizon. Some particles trying to make it out to you won't make it. Accelerating cosmology is like the inverse situation. Space is expanding and accelerating, so some particles trying to make it to you, if it's sufficiently far away, won't make it. You have an event horizon that surrounds you. Okay. Similarly, it doesn't end there. Cosmic horizons seem to have an entropy given by the area of the horizon divided by 4g newton, which was first argued for by Gibbons and Hawking. They also seem to radiate. So you can ask, do they obey a central dogma? Meaning, can you think of the cosmic horizon as some ordinary quantum system with this many degrees of freedom? This was an idea that was first proposed, kicked around by these authors soon after the discovery of a positive CC. And okay, there's lots of things you can say about it. Many of them are cautionary about this being a crazy thing to propose. And here are just a few pieces of the cautionary tale. One of them is that there's little microscopic support for the Gibbons-Hawking entropy. I talked about how for special black holes, you can count microstates in the Hilbert space and reproduce this formula. I think it's fair to say that there's no agreed upon microscopic calculation of this entropy. There are calculations that exist in the literature from different perspectives, but they're all a little fun. Okay. Another thing is that the black hole horizon in the old sense of holography is supposed to sort of encode the interior. Okay, but a cosmic horizon is a little funnier. You can ask, does it encode the interior? Does it encode the exterior? Does it encode both? That's something you sort of have to kind of commit to if you want to think about the cosmic horizon analogously to the black hole horizon. Another thing is that the cosmic horizon is strongly observer dependent. Okay, what do I mean by that? Black hole horizon is observer dependent in the sense that if someone jumps in, they're going to have a different notion of an event horizon. But whoever stays out is going to agree about the horizon. Whereas in accelerating cosmology, different observers at different places of the universe kind of carry with them their own event horizon. So it's very strongly observer dependent, which would make it weird to say that the horizon corresponds to some quantum system. Finally,
And there one other
yeah.
thing, which is that not all cosmologies have horizons.
yeah, accelerating cosmology is one.
Right. Well, I mean, because you have a flat cosmology.
Flat cosmology.
Yeah, basically flat FRW, you never
Yeah.
have even if it's expanded, you never have a horizon.
If it's accelerating.
Well, okay, depends what you mean by accelerating for sure. Coordinate points.
I mean, A dot dot is positive.
Well, okay, but if you look at the conformal diagram of an asymptotically flat, of a flat FRW, there's nowhere to draw a horizon.
But that's a non-accelerating flat.
I think we're talking, use the word accelerating to mean a different thing.
Okay.
No, but there's still an observer horizon, right? Because
being an
when the-
observer, you
when
just want to
observer
draw an
gets-
observer horizon, ascribe plus, and then you just want to draw the path. Yeah, sure.
Yeah.
okay.
Yeah, so that's what, okay, I guess I understand. That's what I was talking about.
It still radiates.
Okay.
There would still be radiation.
You still have causal horizons, because, yeah, but then it's just a regular type of radiation.
And another point, which ends up being a technical point, even though it sounds conceptual, is that in accelerating cosmology, you're stuck in the belly of the beast. The horizon surrounds you, so there isn't really a way to extricate yourself from the system. I mean, there are ways, but they're a little contrived. With black holes, we have the benefit in studying them and kind of being far away from the black hole and observing it from far away. We're not forced to jump into it. In cosmology, we're sort of, the starting point is we're forced to be inside of it. Okay, and that it's raised all sorts of conceptual and technical questions. How do you describe quantum mechanics when you yourself are embedded in the system? It's a mess. So to make progress, you sort of need to separate yourself from the system a little bit. Okay, good. And I'm sure people have their own complaints. Let's encapsulate them in these ellipses here. And I was going to make 2 points, but maybe I'll just make one. first thing I'll say is you can apply these tools that we've been applying to black holes to make some progress on the problem of crunching cosmologies. These are cosmologies that say have a big bang, but at some point turn around and crunch again. Okay, these tools of using the island formula and the gravity path theorem stuff, you can actually use there and find non-trivial islands and make some interesting statements about, you know, holographic style encoding. But that's not, we think, the problem of our universe. So I'm not going to say much about that, but that's a place you can make a little bit of progress. What I want to talk about is something where this feature makes an appearance, and I think is interesting. And it's a puzzle that Adam Levine and I studied. Adam Levine's right there. And let me try and set up the problem a little bit. So here I've drawn the Penrose diagram of Schwarzschild de Sitter. This is going to be analyzed in like a 1+1 dimensional model, which is where we analyzed it. And it has subtleties you can bug me about afterward. But it looks like this. Here's the sort of de Sitter inflating region. Here's the black hole region here and here. And this Penrose diagram is periodically identified. Okay, you could unroll it if you want, but usually it's considered here. And like I said, it's hard to study the system when you're embedded in it. You really want some kind of external view, if you can. One way to construct an external view is to put some sort of flat space region on top of Spry Plus here and think of some observer as like exiting from inflation, the way that like we have, and can kind of look back with a little more comfort, a little more space, and look back at the universe in the past. Okay, this is something you're allowed to consider.
But if you do that, then there isn't an entropy anymore, right?
Yeah, I'm not going to actually connect to A over 4G in a precise way at any point. I'm just going to, yeah. I mean, well, yeah, we can, it's sort of, let me just make a statement. It does actually sort of connect A over 4G, but it's not really the A over 4G of the cosmic horizon. So let me just say the calculation. You can ask about the entropy of some region R. Of some observer who goes up here and can access this region there. And if you apply the island rule, the thing we're talking about, it's true that you will find an island that cuts across this region. Okay, to compute the entry there, you'll find an island here. And this does actually know about the A over 4G, but this is a funny situation where you can talk about this as something like a cosmic or observer horizon for this person, but really it's just a black hole event horizon. So this is another version of trying to compute the entropy for black holes, but the black hole is just in de Sitter space now, or some accelerating space. Okay, so this is, you can do this calculation in 1+1D models. This is the answer you get. That's just a warm-up for the puzzle that I want to introduce in a second. But this should be thought of as very analogous to the black hole computations, not really telling you something about cosmology. Okay, the thing I want to talk about, first, let me draw a slightly different Schwarzschild de Sitter Penrose diagram. I said these regions were periodically identified, so you can actually unwrap it a little bit and add a sort of second region so that you now have two inflating regions and two crunching black hole regions. Okay, classically, this is a fine solution. There are subtleties with dealing with it quantum mechanically, which bug me after the talk because I think it's not super relevant for the point I want to make. And you could consider in the 1+1D models putting a CFT in this theory. And that CFT is going to back react, actually. It's going to back react and change this Penrose diagram in a way that you could compute. In particular, it's going to make the black hole wormhole longer, and it's going to shrink the inflating region. Okay, so the back reaction is going to look something like that. That's important for technical reasons I won't discuss.
That's from the negative energy density.
Exactly. Yeah. In the smaller universe, there are two contributions: the Weyl anomaly and the negative Casimir, which exactly cancel. In this universe, there's an offset. Exactly what it is. Yeah. Okay. Then you can put these sorts of flat space hat regions where you're going to assume that gravity is kind of weak up here, like I did before, so that you can apply the island rule. And you can ask about the entropy of some region for some observer who lives over here. And you can compute in this model and find that there's an island region which cuts across the rest of the universe. Okay. That's actually problematic because this problem is symmetric. There's some Z2 symmetry here. So had you asked about some observer over here, you would get the same answer. If you asked about the entropy over here, you'd find an island region that cuts across the rest of the universe. Now, notice the feature that these island regions overlap. Okay. in the way this problem is set up, this is actually bad. This never happens in ADS-CFT or holography for the problems of black hole evaporation. In the context of ADS-CFT, it's called complementary recovery. Basically says that these, what are called the entanglement wedges, should never overlap. Okay. The reason for that is that, you know, the physical theories here, you can think of the operator algebras here and here as commuting with one another. They're space-like separated, and you can treat them effectively as quantum field theories. And if they can both reconstruct the operators in here, that's going to lead to an inconsistency, because you can take some operator phi, reconstruct it here, take some other operator pi, its canonical conjugate, reconstruct it here. Those two things don't commute in here because they're conjugates, but over here they do. Okay, this is closely connected to violating no cloning. But in any event, this is not supposed to happen. And this is closely related again to the fact that each observer has their own cosmic horizon. You know, if you encode what's beyond your cosmic horizon, the way you encode what's beyond an event horizon, the different observers are going to encode the regions beyond their cosmic horizons, and those regions can overlap. So I think that's a general problem with the observer dependence of the horizon if you want to attach these ideas to it.
Is this any worse than the factorization problem, maybe a CFT? But working on treatment field, sometimes boundaries, they don't look like they have their normal point.
I don't know if it's, I mean, both things are a violation of quantum mechanics, so I'm not, yeah, they're both violations of quantum mechanics. I'm not sure to say which one's worse.
Different, I guess, this time. I mean, we have a film on ADS with other boundaries as well.
I think it's different. I don't think there you would have a situation where these things overlap. If you tried to compute entanglement wedges, you wouldn't find that they overlap. It's just kind of guaranteed by GR. Well, in the classical approximation, it's guaranteed by GR that they won't overlap. So I think it's a little different. It more has to do with the fact that this is kind of like ADS on its side. You're doing things in time. Okay, we don't know what the general resolution to this puzzle is, or if it's even hard to make it super sharp, this puzzle, but I think it's clear that there's a potential issue you can run into. In the models that we looked at, when you define them carefully, it turns out that just the geometry you've been talking about is not the leading saddle point. It turns out that what happens is that the leading saddle point instead wants to split into two different connected pieces of the universe, such that each observer does encode what's beyond their horizon, but only in their connected patch of the universe. So you can compute and see that this contribution beats the other one. So we don't know if this is a general mechanism to dealing with this potential issue, but in some semi-controlled cases, it seems to be what happens. Okay. Yeah.
I'll be curious, when you mean saddle point, you calculate the action, you see which pole of the action is smaller.
Basically, yeah.
What if they're like, what if they're like roughly the same? Like, how do you know?
If they're the same, then usually there's some transition that's about to happen, assuming there's some parameter you're changing.
Okay, but like at late time, one is much larger than others, much smaller than others. Is that the idea?
Yeah,
not necessarily this picture, but in a few different.
that's right. Yeah. Yeah. Okay. I was going to say something about de Sitter space, but I will skip that and just.
Oh.
You see, the tease is always better than what the actual content is. Okay, I'll summarize and then, okay, when someone wants to ask, I can spend 2 minutes in the Q&A talking about it. Okay, so where are we right now from my perspective? I think there are interesting things to study now in quantum cosmology. My best guess for the framework that should be relevant is to have some sort of holographic theory for it. It's something that's been studied since the early days of the discovery of a positive CC. Some things have been learned, but I think we still don't have any single example with a holographic or microscopic description. One reason I'm excited is that I think the gravity path integral, this mysterious object we were arguing about earlier, I think it teaches you about holography. You can ask, why is it producing for you these answers that are, for example, inconsistent with other methods like canonical quantization or quantum field theory fixed curved spacetime? And I think it's because Daniel Harlow and I wrote a paper partly trying to argue for this, is that the answers that it's spitting out for you via the usual rules we think are correct are answers that are appropriate for like a holographic UV completion of the theory. And that's how you should think about what it's computing for you. And in that sense, holography for cosmology is very confusing. The gravity path integral in cosmology is also confusing, but that's something you can technically use, compute things, it spits out answers, and maybe those are clues for what the holographic description should look like. So that's why I'm sort of optimistic in using this thing to learn about cosmology, in particular, a holographic picture.
I mean, you could even say that about the Gibbons-Hawking paper, right? That it gave the aerial law.
Yeah.
Yeah.
I think Gibbons-Hawking were the true discoverers of holography. in
Yeah,
some
I would
sense.
agree with that. Yeah.
And I think from this perspective, lots of, from more general perspectives, lots of new ideas are emerging. People are using matrix models, ideas from black holes, things like that. I think it's an exciting time, and I'll just end with this picture, which for me is the fantasy that I have, is that, the story we tell ourselves of how this picture is produced has everything to do with modes exiting the horizon and freezing and coming back in. And, if there exist these sorts of potential non-local connections between regions beyond and within a horizon, you might dream that this picture is modified in some way that you can test or check. That's a wild fantasy, so don't hold me to it. I'll just stop there. Thanks.
Thank you, Edgar. We have time for one or two questions, maybe.
Yeah, sure. Before I go, any other? Sorry, not just. Okay, time's up. It's a null result, basically. It's just a point that I think is important. It hasn't escaped anybody who I think has thought about de Sitter space and also eternal black holes, that the Penrose diagrams look the same. Okay. All that means is that causal structure is the same. The geometry is totally different, but kind of inverted. And in the black hole case in particular, for an eternal black hole in ADS, which is what's drawn here, there's a way to interpret the bifurcate horizon, its area, as computing for you the entanglement entropy between the theories that live on the left and the right. So here we're using ADS CFT, there are boundary theories on the left and the right, and that bifurcate horizon computes the entanglement entropy for you between those two. It's very tempting, and people have recently tried to interpret this bifurcate horizon in the same way. Okay, it's possible that that is the correct description at the end, but there's one important subtlety, which is that this red dot is what's called a maxi-min surface. What that means is it's a maximum in time and it's a minimum in space. The space is crunching here and here, and it's sort of biggest here. So it's a maximum in time. It's a minimum in space because this is a wormhole that shrinks to the waist here and gets bigger there. So these are called maxi-min surfaces. These are the appropriate surfaces in ADS CFT to compute for you entanglement entropy. Okay, they satisfy all sorts of nice conditions. In particular, the most important one is something called entanglement wedge nesting, which says that as you probe more and more of your boundary theory, you should be able to probe more and more of your bulk or reconstruct more and more of your bulk. Okay, that's effectively guaranteed by these extremal surfaces being maxi-min. This extremal surface is not a maxi-min surface. It's what I'll call a mini-max surface, which says the minimum in time. Okay, space, remember, this is the Sitter space, infinitely big in the past, infinitely big in the future. It's a minimum in time t equals 0. And it's a maximum in space. Okay, it's like the great circle on the sphere or something. So it's a mini-max surface. And we haven't actually interpreted these surfaces even in ADS CFT. They don't really appear naturally. You have to, funny example. Most canonical examples don't have such surfaces. And in fact, the fact that it's a maximum in space causes problems with entanglement wedge nesting. If you try to naively copy a story from here into here and use this to compute the entanglement entropy between two sides, you'd get a totally inconsistent answer. You would find that as you probed more of whatever your microscopic description is, you would access less of the bulk. And that's related to the geometric nature of this surface. So you have to use the surface in a kind of more clever way if you want it to compute for you an entanglement entropy. Since we don't have any microscopic description, it's hard to say anything very sharply, but I think this difference in the nature of the surface is going to play a role in trying to understand what it means. And in particular, I think interpreting it in ADS CFT is a nice open question. Yeah.
But of course, that's DS, not ADS.
Yeah.
Doesn't this fit perfectly with the idea that while space is emergent in ADS, time is emergent in DS? And indeed, if you look at it that way, it's the same, right?
Yeah, in the sense that a maxi-min will become mini-max if you rotate it this way.
And
I don't know how to apply the sort of entangling wedge nesting idea in the DSCFT perspective to see that
No, but
that's even
but-
more, yeah,
Right, nobody knows how to do that, but.
yeah, in that sense,
But it looks right from that point of view.
Yeah.
The diagrams are the same in the sense that the minimum is along emergent. or- yeah.
right, yeah, it's the same I or minus sign that is always haunting us is the thing that's responsible here, yeah.
So let me make a brief comment, which is an upcoming paper, that I'm writing with Jeff and Arvin, where we found these basically these minimax surfaces in generic, fairly generic class of ADS black holes.
Oh, great.
Deep in the interior. And we were looking for a Python's lunch type construction, but these things don't contribute to the Python's lunch. They kind of seem to be totally irrelevant to any kind of microscopic description of ADS-CFT. Can interpret many kinds of QESs, even not just the outermost one, not just the minimal one, but the minimax ones appear to have no role whatsoever.
That's weird.
It's very unusual. And I mean, the other is related somewhat to time emergence, because whenever you have two time-like separated QESs for the same boundary region, it looks like in many cases, not whatever, but in many cases, you get one like that smack in the middle between them.
Sorry, so like for an evaporating black hole?
Stuck on the future horizon, on the computer and passing delivery.
So for an evaporating black hole?
No, so just like just a general non-evaporating black hole
Uh-huh.
with a long wormhole, and you can end up in situations where you have two time-like separated extremal surfaces that are homologous to any either one of the boundaries. And then between them, if you have vertical symmetry, you get one of these, which seems to be related to some kind of time emergence as well.
Interesting. And the fact that it doesn't compute Python's lunch is because it's a minimum in time? That seems to be
That's right. So
related to.
the bulge of the Python can't be
Yeah.
a minimum in time.
Yeah.
Yeah, we should probably conclude here.
Yeah.
Let's thank our speakers.